So what we're showing you right now is waitlist track. So waitlist track is global. It's linked to Open Maps, it's linked to Google Maps, and it has the ability to show all of these different kinds of tags in different locations. So right now this is actually showing the New Jersey Transit trains. So even though we're standing in a garage right now, this is going through the cloud and it's going to jump back and forth between these two different trains, one of which is at the station and one of which is actively running here. And it's running the waitlist technology and it's using the waitlist track. So this is our branded software. So it's really partly a telematics package. It's going to show all of the units that are active in the world. It's going to give you the speed and it's going to give you the health of these units. You see right now that these are live, these are green. And you notice that this is really locked in well, and this is working underground as well. So whether the trains are above the ground or whether they're underground, whether they're in tunnels or whether they're in stations, you're going to get a seamless position. And that is something no one else in the world has ever been able to do. In fact, when we originally, with my company 5D, had done this on trains in New York going underground, they had to close down those subway lines for months to put all of the ultra-wideband at very even intervals all throughout the entire train track. And what we've done here is exactly the opposite. We've said, hey, wouldn't it be amazing if we didn't have to put it throughout the whole tunnels, and we actually could use really good GNSS outdoors when we had satellites. We use the inertial sensor, which is essentially this unit right here. If you look over here at the hardware, that little tiny inertial sensor is going to actually give us very, very, very good accuracy for about 50 meters or so, up to about 100. So if I don't have ultra-wideband units set up and I don't have connection to satellites, that little doohickey right there is going to do me a solid, and it's going to tremendously help me in many regards. Not only is it going to be cheaper from a hardware perspective, it's also just going to be much, much, much easier from a deployment perspective. And certainly for New Jersey Transit, they're like, thank you so much that we don't have to close down our lines. The only place they had to put it to make this work is actually in the stations. And when I say it, I mean these units right here. So if you take a look at these units right here, these are our waitlist anchors. And so for New Jersey Transit, we only needed, I think, 6 of these in a station. And then whatever error has been inherited by our little inertial sensor is essentially removed immediately once the train comes within view of these anchors. Does that make sense? And so you're essentially dead reckoning in the tunnel, you get in the station, boom, you're snapped in, you have this wonderful ultra-wideband positioning, and then you can essentially transform, and the entire time, everything is being done in GNSS space. And so this is waitlist track. Right now the train's going at 21 to 23 miles an hour. It's always locked in. This is jumping to the other train. This is our local display. So Jeff, if you can bring up this local display, just so we can see it visually, you can get rid of this one for right now.
First. There we go. Okay.
So what this is showing us is the data that's running here on the edge. This is what we see coming streaming through. This is our IoT data. It's actually using MQTT. Jeff, what's the latency that we're seeing on the MQTT data?
Locally, you're 3 milliseconds max.
Which is really interesting because our partnership with Z-Telco here uses microwave transmitters. We don't need that to actually calculate the positioning, but we can transmit throughout all of San Diego with only 3 milliseconds of communication latency. So it's interesting that the actual update rate of our position calculations is 3 milliseconds. The distribution of that within our own local environment is 3 milliseconds. And now with Z-Telco, we can transmit that all over San Diego at 3 milliseconds of latency. No one else can touch that. That is a level of latency that is mind-boggling, right? So what you're seeing here is that local data. If I hold here my pedestrian tag, I'm going to see the update on the screen. I'm not sure how well you can see it, but this is me, the blue dot. I'm going to walk this over here, right? And now I'm going to be basically under the eaves here of the house, and now I'm walking it back and you see me come right back to this green dot, which is the other yellow tag right here. And now we put those together. So the main thing here is this includes not only the actual ultra wideband technology, the processor to calculate the position. It's got a battery here that'll last all day from a human safety perspective. But you also have a 900 megahertz connection. And this 900 megahertz connection isn't about getting, again, all across San Diego. It's about having truly reliable penetration all throughout the local environment. So this 900 megahertz is really great. It's much more reliable than Wi-Fi or cellular. It also has almost no latency in that local environment. So that's what's being used here to send that data. And the reason that that's important is if this is a safety critical system, then we really want to make sure that that communication is never diminished, that we don't have latency, and that it's never lost. And of course, as we all know, neither cellular nor Wi-Fi is ever going to give you that, right? And that's why having the 900 megahertz built into this unit is really, really important. And so this is another display here, if you can bring this visualization. So this is more like your facility display. Again, you see the anchors as normal. These are all live, and then you see the two PACCAR units that are updating. And you see they're pretty dang solid. If you really zoom in there, you can kind of see them move a little bit. But generally, that's incredibly accurate and incredibly reliable. And again, you can zoom out with this display, Jeff. I don't know if you have the ability to kind of show us that. And so this is actually Jeff's garage here. A nice little display here. Yeah. And so imagine in the future, we're going to see weightless tags all over the place. And then this is also able to do various macro recordings. I think the other thing that's kind of cool about this is if I do walk around with this tag, it actually traces the route that I take, which is really helpful. And I'm going to walk over to this anchor here. I'm going to walk over to this anchor here, this anchor here. And so you get to see this nice little track. So this is a useful thing. Then I put it back with the other, and you'll see it snap back there. So really, we've been here doing these demos here for an hour or so, and what we find is that the actual system is incredibly robust. You can now see kind of the trail diminish. But this is really important for tracking people, for tracking robots, for just having this awareness of your whole facility. So we call this, right now we're calling it PACCAR. It's just the ability to create this sort of tracking tool for the PACCAR trucks. But this is going to be incredibly important for them for dispatch and for telematics and for understanding a variety of kind of insights about their trucks and about their fleets. Whereas this is really the safety application. With the faster update rates, it's actually able to coordinate collisions and look for people popping out. So imagine really the whole thing is if this pedestrian tag gets too close to this other tag, then you have a problem. And indeed, you can see that the actual physical representation of this needs to be really solid if you're going to do pedestrian safety. And that's why when you zoom in on this and you see, okay, that's rock solid. I can build a safety alert system around this. When Toyota tried to do this with either Wi-Fi localization or low power Bluetooth, what's called BLE, they thought that with about a 1 meter to 1.5 meter error bound, they could still create a safety system for forklifts. Turned out that was rubbish because in the end, the forklifts just alerted all the time, because the position data was bouncing around too much. The pedestrians and the forklifts kind of looked like they were about to run each other over all the time. That's why you need this. You need this rock solid positioning. You see what I mean? You've got these two tags on the ground. You've got these two tags right here. The other thing I want to point out is that this is really suboptimal. It actually works much better when you have it on a real truck or you have it in a static position on a person higher up. So we're actually showing it to you in pretty much the worst possible scenario, which is a guy, in this case, kind of lying on the ground, right? But look at how well that is locked in. The other thing that we wanted to show was essentially how we've solved the indoor-outdoor problem. One of the points to make here is that right now, all of this ultra-wideband is going through the cloud, not this display, but this one. It's also actually reporting in GNSS coordinates. It's in lat-long coordinates. So why that's important is all of the applications on your phone, all of the applications for FedEx and Walmart and UPS, whatever, they're all in lat long. And what we're really doing is we're making the interior, in this case this garage, as if it was in sort of access to satellites up in space, right? And with the accuracy being 10 centimeters instead of 10 meters, right?